You're welcome to today's lecture on ICH 413. So just hold on, let me share the slide. When others come, we'll just admit them to join. Once more, you're welcome to ICH 413 lecture of this week, Petroleum Refining Processes. So what we're looking at today is process flow diagram, PFD. We're looking at the conversion of toluene to benzene. And so we'll see the use of process flow diagram in this conversion process. So process flow diagram, I'll be shortening it to PFD, represents quantum steps up from the PFD in terms of the amount of information it contains. Don't worry about how it sounds now. Very soon you have a clear understanding of this. So PFD contains the bulk of the chemical engineering data that's necessary for the design of a chemical process. PFD, process flow diagram, it contains the bulk of the chemical engineering data that is necessary for the design of a chemical process. So for all the designs shown, the diagrams shown, I'm going to show you several diagrams. And then in all the different diagrams that I use, there are no universally accepted standard for a PFD. So one company can decide to make some slight changes in the information. So even for the process flow diagram that is for the same process in a company, a different company, particular same process, two different companies can decide to make some slight differences. It doesn't necessarily mean it has to be exactly the same. But most PFDs convey similar information. The information they convey are very, very similar. So a typical commercial PFD will contain the following information. I want to show you what a typical commercial PFD contains. So a typical PFD, or in a typical PFD, all the major pieces of equipment in the process will be represented in the diagram. All the major pieces of equipment in that process will be represented in the diagram. I'm talking of the PFD, process flow diagram. You will see all pieces of equipment in that particular process represented on the diagram, along with description of the equipment. The description of the equipment represented there will be given, and each piece of equipment will have assigned a unique equipment number, to have an assigned unique equipment number and a descriptive name. All process flow streams also will be shown, and they will be identified by a particular number. A description of the process conditions and chemical composition of each stream will be included. This data will be either displayed directly on the PFD, that is process flow diagram, or is included in an accompanying flow summary table. All utility streams will also be given. You will see what I call utility streams. So the streams are supplied to major equipment that provide a process function will be shown. Then the basic control loops that illustrate the control strategy that is used to operate the process during a normal operation or normal operations will also be shown. So you will see this in the diagram I will give you. So this is what I'm talking of. You might not understand it at this beginning, but before the close of this lecture, you will have a good understanding because we're going to use some examples, solve some problems using this flow diagram. So let's just pass and go on. But well, you can see the equipment represented here like V101, P101, AB, E, all those are the equipment the identification. And then the description of the equipment, you can see directly under there, like V101 is toluene storage drum. V101 is toluene storage drum. Remember, this process flow diagram, we're looking at the process flow diagram for the conversion of toluene to benzene. So we're going to react toluene and hydrogen, convert it to benzene. And so these are the equipment we're talking of. And then directly under the equipment, you see the description. And then another thing you have to note here is each equipment is the name and description of the equipment is almost directly close to where above where that particular equipment is. So for instance, if you're looking for V101, you will not go to the other end to look for V101 because V101 is just almost directly here, almost directly under where V101 is. So it's quite close to that side. If you're looking for E, or so, looking for, let's say, V103, you will not look at it by the left side. You go almost to the middle and check under there, you will see that particular equipment that is called V103. So let's go on and then you will understand more. This is another process flow diagram. This is another representative of a process flow diagram. You have the hydrogen feed and then the toluene feed reactor and so on. And then let's go on. I'm showing you different flow diagrams here. So, but we're going to use that very figure 1 to solve a lot of problems here today so that it will be easy for you to understand. So this is another process flow diagram. And then this is another one, figure 3 here, still for the conversion of toluene to benzene. So you can see how this one is. So, but let's go on. And so it is clear that the PFD, that is process flow diagram, is a complex diagram from what you have seen so far. It's a complex diagram and it requires substantial effort to prepare it. To prepare it in such a way that it doesn't clutter, prepare it in such a way that one will be able to understand it, one will be able to interpret it. One will be able to interpret it and avoid errors. So often PFDs are drawn on a large sheet or on large sheets of paper. Example is a sheet of paper of the size D, 24 by 26 inches. And several connected sheets may be required for a complex process. So you might have other sheets of paper, other sheets that carry other information that are not placed on the main PFD, on the main PFD paper. Specifically, certain information can be presented in accompanying tables. And only the essential process information should be included on the PFD, on the main PFD paper. So the PFD and the process of interest in this study, what we're looking at is the hydroalkylation of toluene to produce benzene. That's why you see us using hydrogen feed and then toluene feed for the hydroalkylation process of the toluene to convert the toluene to benzene. So that's a particular process flow diagram we are studying today. So this particular flow diagram for the conversion of toluene to benzene is very well studied and is well understood as a commercial process that is even still used today. So some of the PFDs are technically feasible, but not optimized. That means there is still a room for adding and subtracting and improving the process, technology, and also the economic performance. So this allows the techniques to be applied both to identify technical and economic problems in the process. We're going to, as we go on, we're going to identify one problem and we're going to solve it. So, and then to make the necessary process improvements. So because it's not completely optimized that, oh, it must be like this. There's still room for some adjustments to make corrections, to solve problems, to improve the process. So the basic information provided by a PFD can be categorized into one of these three. Process topology, which we're going to look at in detail. Stream information we'll look at in detail, and the equipment information. So as shown in the figure I showed you, the figure 1 or some other figures, 1, 2, 3, I've shown you. The flow diagram as shown in the above skeleton process flow diagram for the production of benzene. The skeletal diagram illustrates the location of the major equipment. So we want to look at process topology now. Process topology. I've told you that the process flow diagram is basically categorized into 3: process topology, stream information, and equipment information. So let's look at the process topology. What is process topology? The skeleton diagram, like the diagram I showed you, illustrates the location of the major pieces of equipment and the connections that the process streams make between equipment. So in this lecture, I'll be going back and forth because I'll be using that figure 1 to do most of the explanation. So I'm going back to figure 1 now to show you what we're talking of, location of major equipment and connection that the process streams make between the equipment. So if you go back, let's go back to the first one. So you see the location of the major equipment, for instance, V101, and you see the process stream connection. You can see here stream 1 connecting to V101. So that is a process stream that you see one there inside a diamond kind of symbol. So that's what we're talking of, the process stream connecting to the equipment. So let's go back to where we are, okay? So, and then the location of the equipment and the interaction between the equipment and the process streams is what is known as process topology. The location of the equipment and the interaction between the equipment and the process streams, which I just showed you, is what is known as process topology. So equipment is represented symbolically by icons that identify specific unit operations. So like that one I showed you, I said V101. And then let's go on and you understand it. Although the American Society of Mechanical Engineers, ASME, publishes a set of symbols to use in preparing flow sheets, it is not uncommon for companies to use in-house symbols. So a company can just decide to use their own in-house symbol instead of adhering to the ASME symbols. They can just decide to use their own symbols and it's known to them, so they can just do as they like. There's something that is understood by them. Okay. So a comprehensive set of symbols is shown below. I'm going to show you a set of symbols for equipment. So whatever set of symbol is used, there is seldom or rarely any problem in identifying the operation represented by each icon. So it's very rare to have any problem of identifying the symbols that are representing a particular process. So the lists of the symbols used in process diagrams as shown covers more than 90% of those needed in fluid or fluid process like gas or liquid processes. So I will show you soon. And so the figure above shows that major pieces of process equipment, figure I showed you before, which I will still go back and be referring to that. That shows that, so it shows each major piece of process equipment is identified by a number on the diagram. A list of the equipment numbers along with a brief description name of the equipment is printed along the top of the diagram, like what I showed you about the V101. See, along the top of the diagram, you see a lot lined up. All those are the different equipment and their different descriptions. The location of these equipment numbers and names roughly correspond to the horizontal location of the corresponding piece of equipment. I will go back and show you that again, even though I mentioned it before. So okay, if you see lined up on top of the sketch there, you see different equipment symbols, and equipment descriptions. So if you are looking at V101, it's on the left, the first there. So you don't go to the right to look for V101. That's why we're told that it's almost horizontally just below what is written about it. So like you see V101, you look for it on the left side. If you want to look at V103, you see V103 is written there, up there, almost like in the middle, thereabouts. You just go down there. It's almost horizontally below it. So that's how you identify and locate where your equipment is. Okay, so let's go back to the slide where we were. So that's what I meant by the location of these equipment numbers and names roughly correspond to the horizontal location of the corresponding piece of equipment. Convention for formatting and identifying the process equipment is what I will show you below. So this is the format, the general format for identifying process equipment. Don't worry about how it looks now. Very soon you're going to use it in today's lecture to solve problems. We have XX, general format is XS-YZZ A/B. XX are the identification letters for the equipment classification. For instance, C stands for compressor or turbine. E is for heat exchanger. H is for fired heater. P is for pump. R is for reactor. T is for tower. TK is storage tank. V is vessel. Y designates the area which the plant is, the area within the plant. So if you go to that general format, you see XX, that is what I've just shown you, XX, you see E and so on. Then we go to Y, is it shows the particular area within that plant where the equipment is located. Then ZZ is the number designation for each item in an equipment class. You will see that very soon. AB, A/B identify parallel units or backup units not shown on the PFD. So then you have some other additional description of equipment given on the top of the PhD. So for now, let me still go back a bit to the PFD to see where we have, let's look for H on the PFD. So let's look for H. So CH here, H101 is a feed heater. The other place is called fired heater. It is feed heater, H101. And you can find it, that H101, you go down, it's not going to be too far. You just look for it. You can find it around this side. So that is it. It's not too far. E103, you find it around here. And E105, you find it by the end because it's at the end. So that is how what we're talking of now. So let's use that general format and really understand better what we're talking of. The general format of XX, we've defined all those now. The table above provides information necessary for the identification of process equipment icons shown on the PFD. An example here is that of P, that is XX-101, that is the YZZ, and then A/B, that is your A/B. It's also same. So now let's explain and understand better these general formats, what it's all about. So in that general format, where we had that XX, YZZ, AB, here we have in place of XX, that is P, in place of YZZ, which is 101, then the AB still stands. So P in that format identifies the equipment as pump. P shows that the equipment we're talking of is a pump. If you go to that PFD, go to that PFD, you will see P, and that shows that that is a pump, and you will see the description also. So now, one, if you look at what I'm showing you, the one that is highlighted is the one we're looking at. In this particular one, the first one is P that is highlighted. So P identifies the equipment as a pump. Then in that format, general format, one that is identified indicates that the pump is located in an area unit of 100, area 100 of the plant. The particular unit in the plant that is identified, that is called area 100, that is where this equipment is located. Now, 01 indicates that this specific pump is number one in that unit 100, is 01 in that unit 100. Okay. Now, AB, as highlighted there, indicates that there's a backup pump. So it means there are two identical pumps. pump P101A and pump P101B. So one pump will be operating while the other one stays idle. So the 100 area, the area designated as 100, will be used for benzene process throughout this text. If you see that PFD I showed, you can see everything is 1 so and so 103, 10. So everything there, this process for the conversion of toluene to benzene, everything is happening within that area of 100 units that is named 100 in that plant. So from one of the figures above, I've shown you like 3 figures. It can be seen that pump P101 is called toluene feed pump. And this name will be commonly used in the discussions that we're using here, and is synonymous with P101. Okay, so during now, we're still on process topology, talking of the relationship between the flow and equipment. So during the life of the plant, many modifications will be made to the process. Often it will be necessary to replace or eliminate process equipment. Like I told you, there is room for modifications to solve problems and to make improvements. So when a piece of equipment wears out, it is replaced by a new unit that provides essentially the same process function as what the old unit was providing. Then it is not uncommon for the new piece of equipment to still inherit the name of the old equipment and the number. So often an additional letter suffix will be added, will be used. Example, if it is H101, now you modify it, it will still inherit that name H101, but it might have another letter suffix, A, added to it. And so it shows that something has been done to H101. And on the other hand, if a significant process modification takes place, then it's usual to use new equipment number and name, complete different modification, changing everything like almost new. So then you can use something really different. Okay. Let's look at an example here. So example here, we have E102. We had a problem with E102, which is to be investigated. In short, there are problems with that particular equipment. E102, nobody knows what the problem is, but it needs to be investigated. So the PFD for the plant's 100 area is reviewed. That is the step to take. And then E102 is identified as the reactor effluent cooler. Let me go back there. E102, let's go and see it on that figure 1, E102. So here is E102 is identified as reactor effluent cooler. So that one has been found to have some problem in that process, and it's going to affect everything. So something needs to be done about that equipment, E102. Okay, so let's see how is this problem solved. So the process stream entering the cooler is a mixture of condensable and non-condensable gases at 654 degrees centigrade that are partially condensed to form a two-phase mixture. This is just telling you what is happening in the reactor effluent unit, how it works. That's how it works. So the coolant is water at 30 degrees centigrade. So these conditions characterize a complex heat transfer problem. So In addition, operators have now noticed that pressure drops across E102, and it's not supposed to be like that. So the pressure drops across the E102 keeps fluctuating wildly at certain times, fluctuates wildly. It's not supposed to be so. And so because of this problem, it's making the control of the process very difficult. So because of this frequency in this problem with this heat exchanger, it's recommended that E102 be replaced by two separate heat exchangers instead of having that one with all the complex conditions that is producing complex problem. They recommend that let's rather use two different heat exchangers in place of that one. So the first exchanger will cool the effluent gas and will generate steam that is needed in the plant. And the second exchanger will use cooling water to reach the desired exit temperature of 38 degrees centigrade. So these two exchangers are now to be put in place to replace E102. So because of this major change that is done, then of course, you know, equipment E is represented, the letter E is representing heat exchanger. So we now have, in place of E102, we now have E107 and E108. Those two heat exchangers. E107 reactor effluent boiler, E108 reactor effluent condenser. So the E102 designation is retired, not assigned to any new equipment in that PFD. So there can be no mistake that E107 and E108 are new units in the process, and that E102 no longer exists. Okay, I believe you understand that. So now, let's look at stream information. We have just looked at process topology relating the flow to equipment. So now, referring back to the figures above, we're going to still be going back to those figures. It can be seen that each of the process streams is identified by a number in a diamond box located on the stream. The direction of the stream is identified by one or more arrowheads. The process stream numbers are used to identify streams on the PFD, and the type of information that is typically given for each stream is discussed in the next slide. So, but let's go back and see a process stream. I say it is identified by the diamond icon, and then you have the flow showing the direction of the flow, the arrowheads, and then you have a particular number in that diamond icon to identify that particular process stream. So I want to go back there for you to see. We're still referring to that particular. So you see the sketch there. You see something that is like diamond there. You can see under toluene there, you see 1. So that is the stream, the process, the stream there. And then it's identified, stream 1 is identified by that. So you see stream 2, stream 6, you see the different streams there. So we also have utility streams. These are the needed services that are available at the plants, like cooling. You know, the chemical plants are provided with a range of central utilities that include electricity, compressed air, cooling water, refrigerated water, steam, and so on. So that is also identified on the PFD. In this case, you'll see it looks like round, and it cross a stroke, and a stroke crossing in the middle of the circle. That's how it looks like. When I go back there, I will show you. Okay. So now these are process stream information, table 2. So we have different streams there. Like I showed you the one just directly below toluene, that you have the diamond there with 1. That is stream 1. So in that PFD, we have 19 streams. Then we have temperature under at each stream. This is what it is. Pressure, and all those other see the other parameters, the different parameters there, you can find them under the different streams. Hydrogen, methane, benzene, toluene, you find them under the different streams. We're going to use these to do calculations any moment now. Okay. We're going to combine this particular stream information with the PFD that we have, the figure 1, and we're going to do calculations soon. So each utility is identified by the initials provided in the table below. As an example, let us locate E102 on figure 1. Let's go back, E102 on figure 1. And before we go back, I'll show you also the utility stream. The notation CW, that is for cooling water, associated with a non-processed stream. It's not a process stream. Process stream, you see it's identified by diamond and a number in it. The utility stream is not so. I'll show you how it looks like. So into E101 indicates that the cooling water is used as a coolant for the E101 equipment. Electricity used to power motors and generators is an additional utility that is not identified directly there on the PFD. Most of the utilities shown are related to equipment that adds or remove heat within the process in order to control temperatures. This is common for most chemical processes. Let's go back and I show you. We'll locate E102 and then we'll locate the utility stream. We're going back to figure 1. Going back to figure 1. So E102 is here. So let's go down below that. We'll be able to find it. You can see E102 down. You can see it down here. And then you see the utility stream, CW. This is CW. So, and that is it. We can locate it here. So let's go back to okay. So now the utility streams still under the stream information. So we have yeah. So now we have everything, all conventions shown in table 1 apply. Everything that is in table 1 apply. That's what we're using. The diamond symbols located in flow lines, numerical identifications, the flow direction shown by arrows on flow lines. So the utility streams that we have there, these are the different utility streams and their symbols and their identification letters. LPS is low pressure stream. CW is cooling water. RB is refrigerated brine, so and so on. So these are the utility streams that you will find there. Okay. Now we have also here required information. The required information when you want to solve problem, you need the stream number, you need temperature, it might be required, pressure, vapor fraction, and so on, total mass flow rate. We're going to do that one Now, any moment now, we're going to solve problem of the mass flow and the total mole flow rate, individual component flow rates. You have other optional information that you might need as shown here. So now we have this table 5. We're going to use this table 5 and we're going to use figure 1. We're going to solve some problems any moment now. So in table 5 is giving us information for temperature at different stream numbers. Then so temperature, pressure, and different at this different process streams. So now we still have several other parameters there under different process streams. Process stream 1, 2 to 19. I told you we have the 19 process streams here in this conversion of toluene to benzene process. So we have all this and there are numbers given to us here. So we're going to use this and do calculations now. So with information from PFD, that figure 1, and the flow summary table, table 5, problems regarding material balances and other problems are easily analyzed. So if material doesn't balance, you know that there's a leakage somewhere. If you balance and everything is okay, as from what goes in is equal to the same value with what comes out, then everything is in order. So it's important to carry out a material balance. So now I'm asking you, we're going to do it together here. Check the overall material balance for the benzene process shown in figure 1. From the figure, we identify the input streams as stream 1, that is where I just showed you not long ago that diamond with 1. That stream 1 is the toluene feed stream. And we have stream 3, hydrogen feed. We're talking of inputs. We want to balance what comes in and what goes out. If it balances, then it's okay, no problem in that process. If it doesn't balance, there's a leakage somewhere. So now let us see the overall material balance, if it is okay. So the input streams we have are stream 1 and stream 3. I'll go back there and show you any moment now. And the output streams we have are 15 and 16. Stream 15 is where you have the benzene as a product coming out. And then stream 16 is where you have the fuel gas that is also coming out as a product. So from the flow summary table I showed you, table 5, the flows, they are listed, the unit is in 10 raised to power 3 kilograms per hour. That is the unit. So now let's see how we can solve the problem. I want to go back there and show you the different feed streams and then the different output streams. So let's go back to figure 1. So you see here, toluene feed stream, the stream is here, diamond 1. For hydrogen is diamond 3. If you look at the input is that round you see with black in part of the circle. And also the output also looks like that, round with black in each. So the input stream 1 and stream 3 are the streams that put in toluene and hydrogen, and then output is out of fuel gas, stream 16, and the output stream 15 is for benzene. I hope you can see that, the stream on the PFD. So let's go back and do the calculation and see input and output using that table 5 and the figures given to us in table 5 if it balances. So Now let's go to table 5. We're now concerned about stream 1 and 3. We're not concerned about any other stream when we're talking of input. So our stream 1 and 3, if you have something, you can write it down, but I'm going to show you in the next slide. Stream 1 and 3, stream 1 and 3 is what we're looking at here, is what is of great concern to us. Stream 1 is where toluene is going in. So under toluene, under 1, toluene is 108.7. Then stream 3 is where hydrogen is going in, which is 286. Okay, so when you add the two, stream 1 and then stream 3, you should be able to have something equal to benzene is stream 15, 105.2. Then stream 16 here is the gas coming out. So let's go and look at how we solve that problem. So here, stream 3, the input stream is 0.82. So input, sorry, we'll go back there and check. The stream for hydrogen 0.82. Stream 1 is 10. So if you add it, you have 10.82 times 3 raised to power. Then stream 15 is 8.21. Stream 16 is 2.64. So let's go and check stream 3 and stream 1. Stream 3, 0.82, stream 1, 10. Stream 3, well, you just use this as okay, it's here. So table 2 is what we have to use. Why are we using table 2 instead of table 5? We're using table 2 because we're looking at the flow balance, the mass flow. So the mass flow is what we're trying to calculate. I think you can see here. So the mass flow, stream 1, we have stream 1, as we saw there in the PFD, is where the mass of toluene is flowing in, the input. So let's look at stream 1 under mass flow. We have 10.0. Then stream 3, also under mass flow, we have 0.82. We're looking at the mass flow balance, the material balance. So 10 here plus 0.82 will give you 10.82. That is what input we have put in from stream 1 and stream 3. Now the output is, output flow is 15, stream 15 and 16. Still under the mass flow, stream 15 is 8.21, stream 16 is 2.61. If you add these two, it will give you 10.82. Let's go and check. Okay, so you see, this is what we had. Because we are looking at mass flow, so we go to the one of mass flow, and then we see here. So it has balance. So input is equal to output. So there's no problem there. So there's another, we're going to solve some other problems. Determine the conversion path of toluene to benzene. What is the conversion? Conversion. In R101, in that figure 1, how do we define conversion? Conversion is simply the in case of benzene here, is the benzene produced divided by toluene introduced. That's conversion. So from the PFD, input stream to R101 as shown on stream 6 and then stream 7. Input stream 6 and 7. And then the output is stream 9. So now this time we're using the table 5. The other one we use table 2. So now let's look at table 5. We're looking at input, output to see the conversion. The amount of benzene we have that is produced divided by the amount of toluene that is going in. So input streams for R101 are shown on stream 6 and stream 7. The output is stream 9. But let's still go back to the table again, or no, the figure, so that you can see what I mean, not just that I'm telling you that input stream is so and so. Let's see. So let's look at R101. Where is R101? So look at R101. Look at R101 here. This is the equipment. The R101 is this equipment. So input stream, of course, remember that the stream, process stream is shown by the diamond icon. So we see input stream 6 here is the input stream to R101. You can see the direction of flow is coming into R101. Another input stream that is also coming into R101 is stream 7. You can see it here. So for R101, the input streams are 6 and 7. What of the output of the R101? It's only one output that is coming out. You can see the bottom of that reactor is the only stream there is 9. So input stream 6 and 7, output stream 9. So let's go back and solve that problem now. So we're using, in this case, table 5. Let's check for table 5, input stream 6 and 7, and output stream 9. So table 5, input stream 6 and 7. Remember that the input is toluene, and okay, so we have here 144.0, and then stream 7 is 0.04. So it means the input stream is 144.7 plus 0.04. That's the input. And then the output, of course, you know, output is benzene. So you go under where you have benzene, and it is stream 9. So we have 116. But we also see that we still have to look for outputs of 6 and 7 there, because there will be some unreacted toluene that will be coming out along with the benzene. So we look at 6 and 7 also. In this case, we will subtract stream 6 and stream 7 under benzene. So those are the things that are coming that are not benzene, that are not converted. So we'll subtract 6 and 7 from 116. That is the output. And then for the inputs, we have 114.4 plus 0 this. So we're going to divide 116 minus 7.6 and 0.37, dividing that one by 114.04. Let's go back and see. So can you see now we have the toluene here, 114 stream 6 and stream 7, 0.04, which gives us 114.04. And the benzene produced, we have seen there on the stream 9, 116. We see that same stream 9 under benzene because what came in, the inputs, those that did not convert. That's why we have minus here, 7.6 and minus this. So that gives us here. So now, conversion is product divided by what you put in the feed. So now this process had a conversion of 0.75. On the other hand, alternatively, you can write the conversion in a different way. You can look at the moles of benzene produced that equal to toluene in minus toluene out. We can still go back there and see. So toluene in, hey, we have already passed the time. So can you just give me some 3 or so minutes, please? So that we can complete this solution. So if you go back, you see toluene in and toluene out. So toluene in minus toluene out will give you the benzene produced. And so the benzene produced now divided by the toluene, by the inputs, which is 144.4, is giving us 0.5. Let's go back there and see that particular one. Toluene in and toluene out. So we still go back there. So toluene in here under stream 6, toluene in, and it's 6 and 7 that are toluene in, yes. Now we go and look at toluene out. The output here. Let's go back there. So toluene out is 36. See it here. Toluene output, where is output is 9. Remember that stream 9 is the output stream. So for toluene that comes out here is 36. So now toluene in minus toluene out gives us 108.04. So you then divide that toluene out, which is the product, divide the benzene produced 108.4 by the input. You still have whichever alternative method you have, we will still end up with 0.75 conversion. So the little problem here is just to sketch. This is the last, second to the last slide. Sketch the block diagram of the production of benzene according to the following process description. You can be given something like this to sketch. We have toluene and hydrogen converted in a reactor to produce benzene and methane according to the following reaction. Reaction doesn't go to completion. Of course, that means you have some excess toluene, like we saw in the other one that went into the product. And the uncondensable gases are separated and discharged. The benzene products and the unreacted toluene are then separated by distillation. The toluene is then recycled to the reactor and the benzene removed as product. So what you can be asked to sketch this PFD. So this is how it will look like. So this is how that particular description will look like in a sketch of PFD. So I think this is the end of the lecture, and I'm going to send the link to you also. As usual, I'll also send the slides also to you in addition. And so